Hi guys, welcome to Pepcoding. So in this video we are going to discuss another new question of our arrays and string series, that is my segmented sieve. So in this question what we have to do, we will be given two numbers and we have to generate, we will be given two numbers a and b, and we have to generate all the prime numbers between a and b, including a and b both, and we have to print each prime number in every new line. Alright, and our allowed time complexity is order of n log n. Alright, which is a bit familiar to us because we have solved that Sieve algorithms, right? So in that, similarly to that, our time complexity should be of order of n log n. Alright, and our allowed space complexity, that is the extra space that we can have, is of order of n, which is again equal to b minus n. Alright, okay, so now let's discuss how we can solve this. Suppose I am given two numbers, a which is my low and b which is my high. So now what do I have to do? I have to print all the prime numbers between these two numbers. So now what can I do? My approach 1 says, that is why I have approach 1. So I call it approach 0. It says that generate all the prime numbers between b and a, between b to a, right? B and a to b. So and print them in new line. So it says generate all prime numbers between b and a, prime numbers between a and b, a and b, and then print them in new line. But it is going to take order of n root n time, because for each number that is from between a to b, we have to run a loop till root n to check if it's a prime number or not, right? So its time complexity is going to be order of n root n. So we are not allowed to use this. Now we'll be using, now let's discuss about approach 2. I call it approach 1 now. Approach 1 is generate prime array. Generate prime array using Sieve algorithm. But Sieve algorithm, let me just remind you, it works for 2 to n, because there we have a is equal to 2. Alright, it does not. Now here we have a is equal to some other number. It can be 2 or more than 2, right? But there we have to print number till 2 to root n, where we were given b is equal to n. Alright, so we have to generate prime array using Sieve's algorithm. So what we used to do in Sieve's algorithm, we used to make an array of size n, right, where my n was equal to my b, which was my upper range. Alright, so here if I say my a, I have constraint like this. So if my b reaches 10 raised to the power 9, if my b is equal to 10 raised to the power 9, then I have to make an array of 10 raised to the power 9, which is not allowed. We are not allowed to do so, right? Because it is a huge amount of memory. So now the second constraint that I have is equal to that my b minus a can be less than equal to 10 raised to the power 5. It ranges between 0 to 10 raised to the power 5, right? 1 to 10 raised to the power 9. The difference between my upper and the lower range, right? If this difference can range from 10 raised to the power 5, then what can I do? It means I can use an array of b minus a size, right? Because it's comparatively lesser than my 10 raised to the power 9. 10 raised to the power 5 is lesser than my 10 raised to the power 9. So we are going to use our second constraint. Alright, now let's discuss about our approach. Okay, now let's discuss about our approach, which is approach 2. Okay, so what am I going to do? First of all, let's say my low is 22 for an example only. My b is 51. My allowed space is b minus a, which is equal to, let's say b is what, 51 and a is 22. B minus a is 29, and we are going to make an array of b minus a plus 1. Plus 1 is not a huge amount, so we are going to make an array of 30. For this, to solve this, to print this prime number till from a to b. Alright, okay, I am going to use an extra space of b minus a plus 1. Okay, alright, now what do we have to do here? I am going to generate all the prime numbers between till root n to root b. N is here b. So I say that generate all the prime numbers till root b. Why root b? Let's say root b here is going to be what? Equal to 7. Nearly equal to 7. So all the prime number till 7 is 2, 3, 5, 7. All the prime numbers are this. Okay. Now what do I say? Now how my array, this is my array which is of size b minus a plus 1. It will be an array of Boolean type where 2 represent my non-prime and my sorry, let me just write here. Okay, now my here my in my array my true represent non-prime, it means the number is not prime, and false represent prime. Okay, alright, now let's make an array of size 30. Let's say I make an array here of size 30. So indexes are going to be 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29. Alright, this is my array. So initially I am going to make the prime factor of these the factors of these prime numbers. So the prime number that I have is 2357 that my Sieve algorithms has generated. Alright, so here the prime, first of all the value here at index 0 is going to be what? It is going to be equal to my A. A is 22 and B is 51. Initially the value at index 0 is going to be what? A. And the value at index, last index is going to be equal to B. Alright, now here A plus I, that is 23. A is what? 22 plus 1 I. A plus I here is 22, which is equal to 22 plus 0. Alright, here it will be 24, 25, 26, 27, 28, 29, 30, 31, 32, 33, 34, 35, 36, 37, 38, 39, 40, 41, 42, 43, 44, 45, 46, 47, 48, 49, 50. Right? Now I am going to mark the multiple of 2, that is my prime of I. That is initially prime of 0. I am going to mark the multiple of 2 to be true. So here multiple of 2 is 22, which is true. I mark it true. I mark 24 true. I mark 26 true. Then 28, then 30, 32, 34, 36, 38, 40, 42, 44, 46, 48, 50. Alright, now the factors of, that is the multiple of my another prime number, that is my 3. Multiple of 3 are 24, 27, then 33, then 36 is already marked true, 39, 42 is already marked true, 45, then 48 is already marked true, then 51. Now prime factors of 5 are 25 is marked true, let me just mark it true, then 35 is not marked true, let me mark it true, then 40 is marked true, 45 is marked true, 50 is marked true. Factors of multiple of 7, 28 is marked true, 35 is marked true, 42 is marked true, 49 is not marked true, let me just mark it true. Now the numbers remaining that are not marked true are my 23, that is my 23, my 29, my 31, then my 37, then 41, then 43, then 49, 47, sorry. These are the number that are my prime numbers in this range, that is from 22 to 51, right? So here now I am going to mark these things true, mark these array elements true, right? If these numbers are true, it means that these are non-prime number, and if these numbers are false, that this is false. This is false. If these numbers are false, it means these numbers are prime number. Okay. Now, if I have to start, let's say I have to mark the multiple of 7 true in this array. So I have to look at this if it's a multiple of 7 or not. Look at this if it's a multiple of 7 or not. Look at this if it's a multiple of 7 or not. It's going to take a lot of time. So I have to search for the starting index from where the multiple of 7 starts. Alright, so my starting index here is 6, that is multiple of 7, that is 28 start from here, because before 27 I'm not having any multiple of 7. So how am I going to search for this index? So now let's see how to calculate starting index for these numbers. Suppose let's learn how to calculate starting index. First of all, as we know, my A is equal to 22, my B is equal to 51. Alright, now how am I going to solve this? Now the formula for this is A multiplied by 1.0 upon my prime of I. Let's say this is my prime array 2, 3, 5, 7. Okay, and take its seal. So seal A is 22 multiplied by 1.0 upon my, let's say 2. Let me just take it, let's take 7. If I take it 7, its answer is going to be something, 3 point something. Okay, if I take its seal, it is going to give me 4. Now it has only given me the multiple of 7. Now I have to calculate the starting index also. So to calculate starting index, my formula is multiple multiplied by prime of I, which is 7 here, minus my A. So multiple is 4 multiplied by 7 minus 22. So 28 minus 22 is going to give me 6, which is equal to my index, starting index, as you can see here, 28. Starting index here is 28, right? Starting index here is 6, which has the value 28, right? Which represent the value 28. Okay. Now again, if I take an example for 5, if I take 5 here, okay, 5 here. So the value of multiple is going to be what? 5 multiplied by 1.0 upon my prime of 5, which is equal to 5. It is going to give me, A is 22, 22 divided by 5, it is going to give me 4 point something. So its seal is nearly equal to 5, right? Now starting index will be equal to what? 5 multiplied by 5 minus 22, 25 minus 22, which is equal to, it is going to give me 3. So now let's see if at index 3 there is a multiple of 5 or not. Yes, at index 3 it represents the starting index where I found the first multiple of my 5. Alright. Now every time I have to jump to my next multiple of 25, I am going to increase my first index, that is my starting index, by prime of 5. If I increase its index by prime of 5, it is going to reach at 3 plus 5, which is equal to 8. So at 8th index I found another multiple of 5, which is equal to 30, right? Okay, so every time I am going to calculate my first index, and after that I am going to increase it by prime of I. Alright. Okay. Now we have talked about how to solve my find my starting index. Now I am going to have a problem here. That is a subtle test case that can be failed. Now let's discuss how. If my A's value was 2 and my B's value is, let's say, 100. So for this, that my array would start from index 0, and at index it represent my value 2. At index 1 it's 3. At index 2 it's 4. At index 5 it's 6. At index 3 it's 5. Right? At index 4, and so on. Right? Now, if at this particular index it's 2, if I'm going to calculate a multiple of 2 here, so my A here is 2. Let's say A here is 2 multiplied by 1.0 prime of I, which is equal to 2, right? It is going to give me a multiple of 1. If I put 1 here, so my starting index would be equal to 1 multiplied by prime of I, which is equal to 2. 2 minus 2, which it means it is going to give me 0. So if it gives me 0, and if I mark it true, it means it represents a non-prime value. But here I lose a prime value because my 2 is a prime number. So every time you get a multiple to be 1, so you have to increase its value. So if I increase this multiple by 1, so it becomes 2. If I put here 2, then 2 multiplied by 2, it is going to give me 4. 4 minus 2, it's going to give me 2. So at index 2, my next multiple of 2 is there. Alright. So if I found my multiple to be 1, I'm going to increase my multiple by multiple plus 1. Alright. You can also see the case where A is equal to 3 and B is equal to 100. Similar case lie here. When? So let's see how. If I put 3 here, 3 here, multiplied by 1.0, prime of 5 is 3 here. Okay, it is going to again give me a multiple of 1. If there is a multiple of 1, then 3 multiplied by prime of 5, which is 3, minus a, which is also, sorry, 1 multiplied by 3 minus 3. It is going to give me 0. So again my array for this would be like this. So again at index 0, I am going to have a prime number, right? So I am going to again lose a prime number. So the main condition, when you find any multiple of any multiple equal to 1, you are going to increase the multiple by 1. Alright? Okay. Now let's try to code for this. Okay. This is my method. So first of all, I am going to make a variable of string type. String sb is equals to new string builder. Let me make a variable of type string builder. New string builder. Okay. Alright. Which is initially equal to, now sb is initially equal to empty. Now what are we going to do? We are going to make an array of type boolean. Let's name it arr. New boolean. It is of size b minus a plus 1. Minus a plus 1. Then there is again an answer array, int answer. Okay. Alright. Now what do we have to do? First of all, it will not be answer, it will be an array named prime. Let's name it prime, which will ask for prime numbers till root b. Segmented Sieve algo. Sorry, there is no method named. We have to write a method also again here that will return me the prime number till root b. So let's name it public static. It is going to return me an array of type integer. Let's name it prime, which is an extended version of my Sieve. So let's write Sieve prime. Sieve Sieve prime. Alright, it is going to give me prime numbers, and there will be passing a value in capital N. Alright. Okay. Now it is going, this method is going to give me all the prime numbers. Alright. So let me write Sieve prime. Sieve Sieve prime. Okay. Now let's pass root b here. So let me just make an variable int root b, which is equals to math dot sqrt. Okay. Now we are going to pass here root b. It is going to generate all the prime factors till root b. Alright. Now in prime, I have found all the prime numbers till root b. Okay. Now I am going to iterate over each and every prime number. So int prime number in prime array. I am going to calculate multiple. So int multiple is equals to, what was my int multiple? It was equal to seal of math. Let me just int math dot seal of a multiplied by 1.0 divided by 10. So divide by prime number, right? Okay. I will check if my multiple is equal to 1. If it's equal to 1, then do what? Multiple plus plus. Alright. And if it's not equal to 1, then do what? Then run a while loop. Then first of all, let's make a first index, starting index, which is equal to multiple multiplied by prime number minus a, right? Now while my fi is lesser than arr dot size, arr is my boolean array. If it's lesser than arr dot size, then make arr of first index to be true and then increment by first index by prime number, right? fi plus equal to prime number, right? Now let's make an answer array, int answer. Okay, now let's run a for loop. Let's run a for loop. Let's make an array list here. Array list of type integer. Answer. Okay. Answer is equals to new array list. Okay. Now I will run a for loop for int I is equal to 2, I is equals to 0, I less than arr dot length I plus plus. I see here if my arr of I is equal to false, and I'm again also going to check another condition here, that is my a plus I should be greater than 1. A plus I should be greater than 1. Why am I checking here? Here let's see. Wait. Why am I checking here if my a plus I should be greater than 1 or not? Let's say I is my starting value, right? If this sum is lesser than 1, then it means my a's value is even more lesser than 1 or maybe equal to 1 when I is equal to 0, right? So it means a is equal to 1 or lesser than 1, right? So we do not have any prime number lesser than 1, right? We have prime number starting from 2, that I'm talking about positive integers, right? So that's why I'm checking if a plus I should be greater than 1. Alright? Okay. I will check here if arr of I is false and a plus I should be greater than 1. Alright? If it's equal to false, then I'm going to add it to my answer. Answer dot add answer dot add a plus I. Answer dot add I, right? All. Okay, so here it will be answer dot add I. Now what am I going to here? I'm going to print my array list, or I'm going to print it in line wise. So for int in my array list, its name is answer, or I can print it here also. Here instead of doing this, adding it to my answer, I'm going to print this simply. System dot out dot println my a plus I. Alright? A plus I. It should be a plus I, not I. Alright? Okay. So here we have to write now segment Sieve prime algorithm. Now here I will be making a boolean array because it's going to it should be boolean. What am I writing? Boolean array. Let's make it arr. So new boolean of size n plus 1. Okay. Now here I will run a loop for int I is equals to 2 I multiplied by I should be less than equals to capital N I plus plus. Now I here, if my arr of I is false, it means if it's a prime number, then mark its multiple for true. For int j is equals to 2 into I, j should be less than equals to n, capital N, and then j plus equal to I plus equal to I. Alright, now here ARR of j, mark it true. And now here I will check if I will run a loop here for int I is equal to 2, I should be less than equals to capital N I plus plus. I will check here if ARR of I is equal to false, then let's make a prime array here. Int prime is equals to new int. Let's give the size n. Okay, because we are not going to have more than n prime numbers, right? If it's a false, then add it to prime of I. Sorry, add it to my prime. Let me just make an array list here of prime. Array list of type integer. Array list of type integer answer is equals to new array list. Alright, now answer dot add this prime number, answer dot add I, right, and then return answer. And now here I am going to catch it into my array list. Let's name it type integer. Okay, so here we will not be needing any string builder type of object here, because we are simply printing our answer here. Okay, now we should try to run this, because here I have found what I have done in this Sieve prime method. I have made an array of boolean type which will store my true false if my number is prime or not. Okay, then I have made an integer array list which is going to store my prime numbers. Alright, and after that I have run a loop. I am going to run a loop from I equal to 2 till root n, and I am going to check if it's a prime number, if it's false or not. If it's false, it means it's a prime number, and if it's a prime number, then I am going to mark its multiple true. Okay, and after that I am going to check in this for loop if my value is prime or not, and if it's equal to false, it means it's a prime number. Then I am going to add it to my array list and then return it to my this method. It is my segmented Sieve algo. Alright, now let's try to run this. Okay, successful, and now let's try to submit this. Okay, submitted. And if we talk about its time complexity, guys, it means, okay, if we talk about its complexity of this method, let's say my marking is like this somewhat: n by 2 plus n by 3 plus n by 5 plus n by 7 dash 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 up to n by root n. Okay, because our loop is going to run till root n only. So if I take n common here, it somewhat looks like this: 1 by 7 plus up to 1 by root n. Alright, which is this summation is nearly equal to log of log n. Okay, I cannot tell you the mathematical proof because it's going to take about 1 hour or more time. So you have to just remember this thing, that this sum is nearly equal to log of n. Alright, so this is the time complexity of this question is order of n into log of n. Alright, even if we talk in terms of 10 raised to the power, even if we take the highest upper range of 10, its answer is going to be nearly equal to 5. Let's see how. If I talk about 10 raised to the power 9, it is equal to 2 raised to the power 32. If I take log to the base 10 raised to the power 9, 2 raised to the power 32. Now if we talk about log to the base 2, 32, which is nearly equal to 2 raised to the power 5. And if I cut this, my answer is 5 now. Okay, so even if we talk about the upper range of 10 raised to the power 5, we are going to get a lesser, very less time complexity. Alright, so I hope I was able to make it clear to you guys. I hope you like this video, and if you like this video, please like, share and comment, and thanks for watching.